Okay, go ahead.
Okay, awesome. So, sorry, there was some echo. Anyway, well, thank you everybody for joining today. After a bit of a break, we are back with random samples. And today we have Mustafa. Mustafa is a research engineer, actually recently promoted principal research scientist. And he, in his day job, um, overlooks the training of large language model. Um, and he's going to present this weirdly titled paper, Hopscotch. It's a very interesting idea. Um, the genesis of the idea is even more interesting. It was literally a corridor conversation um, that happened to work. You will really enjoy it. So let me just give you a quick overview of what we're going to talk about, and then I'll hand it over to Mustafa and I'll disappear. So we have been sort of fascinated by redundancies in language models, especially to say the transformer blocks, right? So we have done many iterations. I think Kai is on the call. We've been thinking about for a long time. What we learned very early on is they almost seem in the middle layers replaceable or interchangeable. Like you could literally swap their order and it would work. You could route the tokens again and again through them. They still work. Somewhat sort of intuitive because they generate in a manner of saying weights as a function of the data. But then what Mustafa and I don't see Li Gong here and team did is they went and said, well, I mean, this kind of also maybe is saying that there are some redundancies. So let's see how much of those blocks can we get rid of. That's the theme, right? It's going to sound very interesting because we're in a business of making language models very efficient. So with that, I'm going to hand it over to Mustafa. Take it away.
Awesome. Thank you so much. Can everyone on the call hear the room okay? All right. So thank you all for taking time to join us on this Friday morning. Hopefully your day is going well so far. I know it's been a while since we did a random samples talk, so I'll try my best to make this one worth your while and keep it interesting. So today, like Akash said, we're going to be talking about Hopscotch, which is a method that we've been working on specifically for trying to identify and remove redundancies within a language model and seeing how far we can really go in pushing the model to be more and more efficient by means of removing entire blocks. So before I go too deep into the method, I want to start with a bit of background. So just as a quick recap, I know most of you on this call are probably very familiar with language models at this point, but I want to just kind of go over the structure very quickly because it's going to play well into how we're modifying the language model, as well as might explain why we have the title we do for the paper. So to start, at the risk of sounding overly reductive, a language model is just essentially a stack of decoder blocks, or in this case, we'll call them hidden layers. It's quite literally the layers hidden in between the input and output of your model. So what are these hidden layers comprised of? In any given hidden layer, you've got an attention block and an MLP block. So what this means is for your input to the hidden layer, or what we will call the hidden state, it will pass through the attention block, and then it will subsequently pass through the MLP block. Now, there's another component to the hidden layers as well, which we'll refer to as the residual. So in order to avoid issues with, say, vanishing gradients, staying grounded to the original input, keeping that information there, in addition to the output we'll receive from each block, like the attention block or MLP block, we'll also retain the original input, and we'll combine the two when moving on to the next block. So essentially, what that means is as you traverse through a language model, you're going to be going through each block sequentially, step by step. So you're going to go through attention plus the residual, then MLP plus the residual, attention plus residual, MLP plus residual, and so on and so forth. So that is how data is going to pass through a language model. you are going to be jumping through each of these blocks sequentially until you get your output. Now, I'm going to say something that I'm willing to bet is not very surprising to anyone who has worked with language models in recent history, and that is that they aren't very efficient. So, I mean, I'm sure you all know, we've got 70 billion parameter models that perform worse than new 20 billion parameter models. We've got models hundreds of billions of parameters that can't even do addition or multiplication correctly, whereas we have 1.5 billion parameter models that seem to do a pretty good job. So it seems like despite the recent innovation and how language models have continued to improve, they haven't been perfectly optimized along the way. And this is something we can see with a lot of common techniques today. LLM efficiency is a very big field, and a lot of people have been focused on, given these blocks in a model, how can we compress them? How can we make them smaller? How can we get the same amount of information out of them with a smaller memory footprint? And so common methods you might have heard of in the past, like quantization or model pruning, try to target this in different methods. They'll go into the matrices and they'll say, can I reduce the data types? Can I make it smaller so we have more efficient computation and less memory footprint? Pruning will say, can I go into these matrices and remove elements from my computation? Can I make my computation more sparse, and can I make it more efficient? We're going to try something a lot simpler in this paper. Rather than going into the individual blocks and trying to make them more efficient, we are asking the question, are all of these blocks even necessary? So in our case, we're really wondering, what if we were to, instead of going through every single block in the model, what if we were actually able to kind of skip through the blocks? What if we removed blocks from our path through the model and only targeted the ones that were necessary, trying to eliminate redundancy while maintaining the information contained in the model? So this is where the idea of hopscotch came from. Essentially, our goal is to optimally hop through the blocks in a model to make it to the other end as quickly as possible without losing any information. So here's the interesting piece. As it turns out, specifically when it comes to attention blocks, there is a large amount of task-specific redundancy. So what do I mean by this? For a given task, let's say you're working in a math domain, or you're working specifically on some knowledge, there's going to be attention blocks that are contributing more or less the same information to that task. And so what happens is when you remove those attention blocks, it turns out the information loss in the model is actually not very significant. You're able to remove attention blocks from a model, and in most cases still retain a majority of the performance. Now, why does that matter? Attention blocks are especially interesting in this case. When you look at a model's total weights, the attention blocks actually only make up about a third of the weights, whereas the MLP blocks make up about 2/3. So you might be thinking, attention block doesn't matter too much if we're removing it, we might get some marginal gains. But it's important to note the actual computation cost for attention is much higher than that for MLP. Think of it like your MLP block is standard linear O of n, whereas your attention block may be O of n squared. So in reality, your attention computation will be around more than twice as time consuming as your MLP computation, even though it's got half the parameters. So if we're able to effectively remove attention blocks from a model, we actually see a substantial inference time improvement. Now, that's all well and good, but if my presentation was just remove attention blocks, it works, it wouldn't be a very interesting method. And in reality, it's not going to be as simple as that, unfortunately. So what do we actually need to address in order to develop a method where we can effectively remove attention blocks from a model? There are two core problems. First, just randomly skipping attention blocks is not going to get you very far. You might not destroy your model, but the performance is going to significantly degrade if you're just picking out blocks at random to remove. So they have to be selected very carefully to ensure that you have minimum information loss once the block is removed. The second thing, which is more important and something that's been overlooked in prior works, is that even though skipping blocks won't kill a model, it'll still hurt a model slightly with each block removal. You can think of it as the jumps between blocks just getting slightly harder every time one is removed. And so the first point here is probably more self-explanatory, but the second point I'm going to elaborate on a little bit just so that it makes more sense intuitively. So to address these problems, we're going to first implement an iterative greedy algorithm to optimally select the blocks to remove. But second is we're going to be stitching these blocks closer together after removal using a minimal added set of scaling parameters. Now, what does that mean? So, on the topic of trainable scaling parameters, what are we doing? This is why I did the recap earlier on how is a decoder block actually structured, because that's what we're going to be modifying with our method. So we're going to be adding 4 trainable scaling parameters to each hidden layer in the model. 1 for the output of the attention block, 1 for the output of the MLP block, and 1 for each residual in the block. So in total, we are adding 4 parameters per hidden layer to our model. If you say, let's say you have Llama 8B model with 32 hidden layers, that's a total of 128 parameters being added to the model. Now, why exactly are we adding these scaling parameters to the model? Well, in reality, the residual alone isn't enough to account for blocks being missing when we remove them. It's going to help with that original information retainment, but it's not going to help bridge the gap when you have to go from the output of an MLP block to the output of another MLP block now that we've removed an attention block. Essentially, there's going to be a distribution shift that we have to account for. And so what our scaling parameters allow us to do is bridge that gap. We're going to account for the distribution shifts in order to make sure the data still flows smoothly through the model. So an easy way to think about it is like when you have the output, let's say you've got an attention block. It's going to do some transformation to your model. Now it might turn out, or to your data, sorry. Now it might turn out that the information it's adding during that transformation isn't all that interesting or useful. But regardless, your data is shifting from some input to a new output in a slightly different space. And so the next MLP block is still expecting your input data to look like that shifted data after the attention output. So while we don't care about the information in the attention block, we still need some sort of scaling factor to just shift the data over to where the next block is expecting it to be. That's the idea behind the scaling parameters. So now we get on to the main piece. How do we actually identify what blocks to remove in the language model? So step 0, we need to have data. So the process of selecting our candidate attention block to be skipped is really a data-driven process. What we're doing here is we're targeting performance recovery or performance retainment on a specific task. So in our testing, what turned out to be the case was that when you remove attention blocks, the domain that suffers greatest was actually math. And we tested on a wide variety of domains and different challenges. And we saw whenever you remove attention blocks from a model, its math performance tends to struggle very heavily. And so to drive our block selection, in this case, we utilized GSM-8K, which is a math data set. Now, how are we using that data? Obviously, we're not just gonna take a data set and try to train a model with 4 parameters. It doesn't really make sense. What we need to do, it's essential that we use samples generated from the original model's distribution. So what that means is, given that GSM-8K dataset, we'll take the questions and we'll generate answers to those questions using our original model without any blocks removed. That's because our goal is essentially to recover that original model distribution. We're not trying to learn new information or improve a model. We're just trying to retain and recover a model's output. So training only 4 parameters per layer, you're going to struggle a little bit if you're trying to learn new things. But in order to retain the model's performance, it tends to be very effective. So you can see here we have some numbers. What happens when you're doing Hopscotch with the model ground truth data versus just trying to use the data set directly. You can see while we have a lot of success using the model's generated data, it struggles a lot if you're just trying to throw in new information and get it to learn something. So once we have this data, we get to the core piece. This is a very simple method for selecting the blocks to remove in your model. Now, essentially, this is how it breaks down. You're going to loop over the number of blocks you want to remove. So for every block that you'd like to remove, let's say I want to remove 7 blocks, we'll do this process 7 times. For each, you're going to try removing the attention block from each hidden layer that hasn't already had its block removed. You're going to do a single pass of rescaling. And what I mean by rescaling is training those scaling parameters with 1 pass of the model-generated data that we collected. And then you're going to record the average cross-entropy loss over that pass. And you're going to repeat this for every attention block in the model. Once done, you're going to select the block with the minimum average cross-entropy loss as your candidate. And that's the block that's going to be removed. So you'll have 1 block removed. Then you repeat the process. For the remaining, say, 31 attention blocks, you're going to try removing each one, look at the average loss when that block is removed, and now select the minimum average block again. We're taking a greedy approach, but it's important that it is an iterative greedy approach. So why does it need to be iterative? Let's use this scenario as an example. We're going to say we'd like to remove 2 attention blocks from the model. Now, if we do that first pass that I described, we go through each attention block and find the loss. We'll say, hey, the first block gives us a loss of 0.3, the second 0.15, the third 0.1. So if we're doing this in a purely greedy approach, we'd remove the second and third block, right? Now, here's the issue. When we do that, suddenly we see an average loss that's much worse than we expected. We remove 2 blocks, each one individually wouldn't have harmed the model too much, but when removing both, it seemed to actually make a big impact. This is because the information contained within these blocks is not independent. In fact, it's highly redundant. That's kind of the point of the method, is we're trying to identify redundant blocks. So in this case, what ends up happening is we accidentally remove 2 blocks with very similar information, while the third block might have contained some more unique information or different information. So the reason that we do this iteratively is to avoid these cases. Let's go back now and say we only removed the first block and then we reevaluated. We would have seen that the first attention block here, the loss stays about the same because it's not very overlapping with the other 2. Whereas the second block, which contained very similar information to the third block, now is critical because it's the only block in that model containing that information. We want to remove redundant information, but we have to reassess whether other blocks are still redundant once a block has been removed for the model. This is why we take an iterative approach to the block removal. So the next question is, all right, we understand how to remove blocks from the model, but when do we stop removing blocks? Now, the answer to this question is going to depend a lot on the model that you're removing blocks from. For any given model, there's going to be a period of the block removal where the average loss is going to increase linearly. After this, there's going to be a period where the loss increases exponentially. So the target for any given model with Hopscotch is to stop at the elbow. For a 7 billion or 8 billion parameter model that we've tested with, this could be anywhere between, like, say, 4 attention blocks removed in the model to 7 attention blocks removed in the model. Approximately, you're getting like 1/8 to 1/4 of the total attention blocks removed. Whereas once you scale up more, let's say for a 70 billion parameter model, you might not hit this elbow until like 20 or 30 attention blocks in. Prior works have even shown that you could remove up to 50% of the attention blocks in a 70 billion parameter model and still see no significant performance degradation on some tasks. So once that's done, once we've removed our blocks and carefully selected which ones we're removing, it's time to use those scaling parameters to bridge the gaps that we've created in our model. So once the selected attention blocks have all been removed, our final step is to do a more thorough multi-epoch rescaling run, which means passing over that model-generated data multiple times to train the scaling parameters per layer, given those blocks removed. Once you've done that, you've got your new updated model. It's got, let's say, some number of attention blocks removed from the model. It's now smaller, runs faster, and in theory, performs the same. So, how does it look in practice? The answer is pretty good. Otherwise, we wouldn't really have a paper on it, right? So, we see with Llama 3 8B, we can remove up to 7 attention blocks from the model entirely, and using our method of selection, rescaling, we're able to recover, like, on average, 97 to 98% of the overall model performance, even on more challenging benchmarks, which means in reality, in your daily use, it's probably going to be even more similar to the base model. But if we look specifically at the task we targeted, which was GSM 8K, our math challenge, we recover on flexible extract about like 95 to 96% of the performance, even with 7 attention blocks removed out of the 32 total attention blocks. And we notice also on strict match scores, it actually goes slightly up. But the interesting piece here is on other domains, we also see similar recovery. So even though we didn't train on these domains, for tasks like Arc Challenge, GPQA, Social IQA, PAUSE-X, which all cover a bunch of different model tasks. Some are more focused on like reasoning, question answering, PAUSE-X is multilingual. We see that we still retain and recover performance across the board. So we're able to remove these blocks pretty effectively without seeing any significant damage to the model. Now, how much of that is Hopscotch and how much of that is just being able to remove attention blocks generally? So to look at the breakdown, we've got a few different baselines here. The first baseline is just what happens if you randomly remove attention blocks from, in this case, we targeted the middle of the model since we knew it was most likely to be safe. The second case is those same attention blocks removed randomly, but this time we've added the Hopscotch scaling parameters. The third is what happens when you just use Hopscotch's method of block selection instead of randomly selecting the blocks to remove. And the fourth is using the full Hopscotch method. So that's using our method of block selection paired with our method of rescaling, using those trainable scaling parameters. And then your final line here is simply the original model's performance. As we can see across the board, even when you remove attention blocks kind of pseudo-randomly, you don't see a significant drop-off in performance in a lot of cases, except this math case in the center. So you see here, we go from like 83% performance on GSM 8K all the way down to 64%. So we've taken a big hit on the model's ability to do math. But through Hopscotch, we're able to recover a large chunk of that. So instead of going from 83 all the way down to 64, we instead go from 83 to 81. And in the strict match scores for math, which is the domain we trained on, we actually see slight improvement from the original model to Hopscotch, whereas we did see degradation when just removing those layers. So it's also important to note the Hopscotch method, even though it's trained on the math domain, it's not just that it's not killing other domains, it's actually improving in other domains as well. Meaning there is some ability here to generalize on this task of redundancy removal and rescaling in the model. So across the board, for ARC Challenge, GPQA, Social IQA, POSX, we see an improvement from our original block removal to our Hopscotch full method block removal. Now, how does this compare to the field? You might be thinking, all right, so maybe this isn't a super challenging task. Maybe other people have got it down. Well, if we look at other state-of-the-art methods before Hopscotch, we see that there's actually an interesting story here. When it comes to math specifically, you can take a look at the results for 4-layer and 7-layer removal, and you'll notice that the model's performance drops rapidly as you continue to remove more blocks. Additionally, you'll see across the board with the other benchmarks that Hopscotch performs better than the rest of them. Now, why is that? So there's two critical pieces here that prior methods are missing. First, with short GPT, they didn't target specifically attention blocks. They were willing to remove both attention and MLP blocks, whereas we had realized that attention blocks were the ones that carried the mass majority of redundant information, and MLP blocks tended on average to be much more critical to the model's performance. The second piece that played a big role here, aside from maybe more careful block selection, was the rescaling. So none of the prior methods that had attempted to remove attention blocks from a model had this rescaling parameter component. And this was critical in maintaining model performance in challenging tasks like math as we continued to remove more and more blocks from the model. So why does this matter? Why are we removing attention blocks from a model? Why do we care that it performs the same? Why do we care that it's getting small? Like, what's the point? The point is, with every attention block removed, you actually do see a significant impact on inference time. So this is with the llama model that we were showing numbers with just before, and how the inference time cost changes as we remove attention blocks. When we remove one attention block, or for any given attention block, we gain about a 2% inference time reduction. And so when we go to 4, we get an 8%. And when we go to 7, we get about a 14 to 15% reduction in our inference cost. But it's worth noting this is also just the inference cost given the same data with the same batch sizes. We're also shrinking the memory footprint of the model, meaning you can fit bigger batches as well. And so you can kind of continue to expand upon this to see, like, in reality, you might get a 15 to 20% inference time improvement when you remove 7 attention blocks. Now, it's important to note here, on its own, this would be okay. It'd be a pretty interesting thing, but it wouldn't be anything too crazy compared to some of the quantization or pruning techniques that we have today. But the key point here is that this method is fully compatible with any other model compression methods. So this is an orthogonal method, right? With Hopscotch, we're removing entire blocks from the model. And with pruning and quantization, we're going within the remaining blocks of the model and then making those more efficient as well. So Hopscotch can be used alongside quantization or model pruning in order to stack these benefits pretty like orthogonally. There won't be compounding issues. And we've actually done these experiments, and in the full paper I have the numbers to show that Hopscotch plus state-of-the-art quantization works hand in hand together. So you can think of this as a third axis on which we can try to compress models.
We actually have a question we sent from the chat. It's kind of long, but I can read it. So, or Edward, if you want to unmute yourself, you can ask the question.
Okay, yeah, sure, thank you. So I was just kind of looking back to the performance stats of the prior pages. And basically you said that, the performance recovery of GSM-8K, is very important, but you also noticed that there were side effects of like the other evaluations also having similar, 98%, 97% recovery. So wouldn't that indicate that like GSM-8K is, the most suitable for performance recovery or the rescaling, and the others are less suitable? You kind of mentioned earlier that when you had tried sampling the other ones, it wasn't doing as well. So does that kind of imply that GSM-8K has the most complexity in terms of what kind of distributions you're looking for, in terms of what attention blocks to drop and how you would rescale? And if so, could you perhaps convert this into some sort of complexity metric for these different evals based on its performance with Hopscotch?
So for the first part of your question, yes, definitely. I mean, that's why we ended up using GSM-8K as that recovery data set. Because we saw the biggest drop in performance, it also served as the best data to recover performance. And so when running through the Hopscotch method, we specifically used GSM-8K for recovery because it allowed us to bridge the gap across the board furthest. If we were to use something like GPQA or social IQA, we wouldn't recover as much because there wouldn't be as much of a gap to close. And so if you look back at GSM-8K after doing the recovery with a different data set, it wouldn't have recovered as much. And so definitely your intuition is right that because that was the largest gap, it also served as the best data to use when doing recovery for the model. Now, to your second point on complexity, I think the point you made about the metric is definitely doable. I mean, we've even got like a measurable gap here on how much the model is affected in GSM-8K versus everything else when you remove those blocks. So it certainly is measurable by that logic for how much of a gap you see when you remove certain domain, or when you target certain domains during removal. And it could be used to build something more general, where we could define a metric based off of this gap to then go through different domains and determine how difficult is it to retain that information when removing blocks. Now, the piece on complexity is like complexity in terms of model distribution and how that information lives within the model might depend on a couple of things. So it could be the case that GSM-8K is very complex compared to other things, and it requires a bunch of different components in the model coming together and providing different information to solve those problems. It could also be due to the way a model was trained, though. Let's say there wasn't a significant amount of GSM-8K data. It was trained very lightly on it, and so its information is fragile within the model. Whereas if you had maybe trained very heavily on math for the model, perhaps it could be more redundant throughout the model. So it's not necessarily the case that it is simply more complex, but it could be. There are a couple of different things that would have to be explored, and it might actually be a very interesting extension to explore to understand are these twin axes of task complexity and the familiarity with the task useful for determining how much of a gap you're going to see. But yeah, generally your intuition is on point there.
We also have another question from the YouTube. Which models have the greatest redundancy?
So what we've seen is that kind of the bigger you go on average, the more redundancy you get. So like if we go back here, for like smaller models, 7 billion, 8 billion parameter models, there tends to be a good chunk of redundancy, but nothing crazy. You might have like, let's say like 20 to 30% of the model is maybe removable, like the attention blocks. Whereas with bigger models, like 70 billion parameter models, you might see that up to 50% of attention blocks can be removed without significant degradation. So you might be able to really remove like 20, 30 blocks from a model and see similar performance. Now that being said, this is on average. So actually the slide that I'm about to get to will highlight that even when models have the same number of parameters, your ability to remove blocks will vary based on how the model is trained, how many hidden layers the model has, and the general architecture used. So this is a good segue into this next point. So why is Hopscotch interesting? Now, some models, when you do like an SVD analysis, so singular value decomposition to understand how much each block in the model is actually contributing or changing your input, you'll see that some models have a lot of blocks that aren't actually contributing much at all. So like your input is very similar to your output after going through that block. And so if we look at one of the older Granite models, Granite 3.08b, you'll notice that there's like 6 layers here where the attention block isn't actually changing the model information much at all. And so in this case, for Granite, we could actually remove these 6 blocks for free. We look at these 6 blocks, remove them, the model works pretty much the same. Now, with newer Granite models, this isn't the case anymore, but for this older Granite model in specific, it was the case. So here, it's almost an uninteresting problem, removing blocks and how to rescale blocks. I'll reiterate, it's an old Granite model. It no longer reflects the current state of Granite. No further comment. But the point here is that within the same number of parameters, for this Granite model, we could have maybe removed like 10 or more attention blocks and still seen no significant performance degradation. Now, what was interesting with Llama and why we chose Llama as one of our actual like evaluations for our method is because when you do this same analysis, you notice that there aren't layers that have insignificant contribution to the model's input. So across the board in the Llama model, every attention block and every block generally had a similar level of like input augmentation. The data was being transformed to some degree after going through each layer. And so the task of figuring out what layers are redundant and what layers you can remove became non-trivial. And this is why Hopscotch in particular is interesting, because a lot of prior works capitalized on identifying trivial layers to remove within a model. Whereas for Hopscotch, we're saying, even in the case of non-trivial attention block removal, we can still identify and remove the redundant blocks in your model. And so that's pretty much all I have today. We do have a preprint for our paper up and available now, so please feel free to check it out. If you do have like specific questions or things you think of, or if you want to try out the Hopscotch method, or you want to try experimenting with it, or you have an idea that you might want to work on based off of it, please feel free to reach out. We will be actually putting out an open source library for you to play with all of the Hopscotch stuff, but due to anonymity rules and whatnot, it has to wait for a little. But yeah, that's all I had for you today. Feel free to reach out if you have any questions, and I appreciate everyone taking time in their Sunday to sit down with me and learn a little bit about language model redundancy.
We have one question. We have a bunch of questions now, but one from the YouTube. One, it's Friday, not Sunday. That's a couple comments, but two.
Oh, did I say Sunday?
I thought someone might be watching it on a Sunday.
Yeah. So in the case that you're watching this 2 days from live.
So first question from YouTube is, what future research questions did this work open up?
So there's a lot to go on here. I mean, to start, we kind of put this out as a discovery of the kind of ways you can remove blocks from models and what you can do to remedy that block removal. But this is by no means the end state of block removal in a model. I think the actual process of block selection can definitely be iterated upon. But even more so, I think an interesting point is the way that we're doing this rescaling. We've found a method that works for us to account for distribution shift, but it's not necessarily the case that this is the ideal way of replacing attention blocks. And there have been actually other works that have tried to do different techniques for block replacement in a model. So some people have done more heavyweight, what happens if we swap an attention block with another linear layer? Or what happens if we try to change the architecture and fill gaps more robustly within a model? There's a lot to go off of in terms of how do we replace components within a model, as well as how do we choose what components to replace, that I think can be expanded on a lot. Other than that, I think there's a lot to do with understanding the redundancy in these models. The question that we had previously just on like complexity metrics and understanding how these redundancies are represented in the model is a very good place to start. I mean, just here we're saying, hey, we've noticed there's a lot of redundancy in language models, and we found a pretty good way, a pretty simple way of removing a good amount of it. But there's so much that can still be explored on how these redundancies form, how to avoid redundancy in the first place, and given these redundancies, how to better understand where they lie and how to replace them. So there's a lot to be done here. This is just kind of our knock on the door, say, hey, let's start looking at this a little more closely.
Next question is, have you tried this with other model modalities?
Not as of yet. So everything that we've done currently is specifically with like causal language models or like decoder only models. So any sort of autoregressive model like llama models, Quen models, Mistral models, GPT, Claude, etc. Like these language models predict like next token prediction models are the only thing that we have experimented on thus far. But that's not to say that this wouldn't hold true for any type of transformer-based model. And actually, the inspiration that we got from this was Li Gong had found a paper on diffusion models that was using a similar scaling technique to try to enhance the like produced image clarity or quality or the level of detail. And they were using a similar technique where they'd attach scaling functions to the residuals or skip connections, as they called them, within these transformer blocks. And so this could be applied very clearly to any sort of transformer architecture. But as of now, all of our results are on language models only.
We have another question from Edward that I can read that said, I saw briefly you compared with Quen. Was that Quen 3? Does this method work with MOE models, perhaps with different numbers of blocks to remove, perhaps? Expert.
So the numbers that we had and we have in the paper are with Quen 2.5 7B instruct. So unfortunately not Quen 3. That being said, the answer is in theory yes for MOEs. It's something actually could be an interesting extension to test. We haven't tested with MOEs ourselves, but the method itself is functional for MOEs just the same as it is with regular models. So when we have the code open, if you want to give it a try, feel free. We might also try it ourselves, and if we do, we'll let you know.
Sheesh here.
Yeah.
So what are the efficiency gains on an average if you remove one block, like how fast the model
Yeah.
will do inference?
So it's going to depend on the total number of layers you have in your model. So for example, this was with Llama 3 8B. This is a model with 32 hidden layers. And for each hidden layer, the attention block is about 2/3 the cost of the inference time. And so when we remove one attention block from Llama, we get just a 2% boost, 2% inference time reduction. When we go up to 7 blocks, which was where our elbow was for Llama, we get about a 14 to 15% inference time reduction. We also do get a memory reduction as well. So in addition to the inference time reduction, the model is slightly smaller. So in reality, you could fit more data in, and you might see an even further gain in inference time. But for smaller models, this is around the expected gain for this method. When you go bigger is when you see much bigger gains. So for example, like when we were talking about 7dB models. So when you take a 7dB model and you end up removing half the attention blocks, then you're seeing what, like 40-ish% gain in inference time efficiency. And similarly, you can go even further on some of these blocks. You can get up to like 50% inference time gains. So in reality, the inference gains are pretty substantial, but as you might know, it's compared to like quantization techniques, you might gain a lot more because the whole model is becoming smaller. So this is why it's important that this method is compatible and orthogonal to quantization. So
You can apply it to quantized models as well. Right?
Yes, and we've actually tried both ways. So Nikhil actually produced numbers for quantization first and then Hopscotch, as well as Hopscotch first and then quantization. And you gain like perfectly compounding inference time gains while also having no compounding loss. So your loss is going to just be like the sum loss of what you're losing from quantization and what you're losing from Hopscotch. So with methods like GPQ today, where you can do an 8-bit quantization and have like nearly lossless performance, when you apply Hopscotch, you'll gain no additional loss other than like the 2% from Hopscotch on top of that. So it won't get like worse as you quantize or worse as you compress.
Does it matter what order it's applied in, or
Works both ways. So these are purely orthogonal. One is targeting the blocks that remain. One is removing blocks entirely.
So do we have any plans to, so essentially a new model after removing blocks? So upload them to Hugging Face in our AI org?
So in theory, yes. We haven't actually tried that yet. The one thing that is worth noting is because we have this slight architectural modification when we'd have either like we have a transformers where we've added these parameters into the actual model architecture. So you'd either have to use that, or if we could contribute the option of attaching scaling parameters back into regular transformers, then we could have directly usable models that we could upload and use. But as of now, it's currently just within our own fork. So
is it possible to attach a modeling class? I know back then Hugging Face would allow you to do it. With the weights, you can attach a modeling class, but I don't know if they still let you do it.
Not sure. The way that we did it was like directly within the decoder block.
that's right.
We just added these parameters
Yeah.
and then used them in the forward pass.
Yeah.
I'm asking all this because we are doing a lot of POCs, and the Llama 370B model is a very popular model.
This is a model that serves as a very good candidate for this.
And if there are such large efficiency gains to be had with very small, with relatively very high accuracy recovery, I think we should look into exposing it more.
Yeah, it's something we can try out ourselves too. And maybe we can get an artifact prepared for long.
One more question from the YouTube. You mentioned exploring why the redundancies happen in the first place. Do you have any theories?
Theories? I mean, the simplest one is models are bigger than the amount of information we're putting into them, right? So our models are not being fully saturated. And especially when we want to target specific tasks, like a lot of people want their models to be good at math, they'll train on a lot of math data. And so kind of naturally almost is the model is going to learn that math really well. It's going to learn it a lot. It's going to remember it in a bunch of places. And it's going to turn out that it doesn't need to have that much just pure math data maybe sitting, or maybe math is the wrong case because that was the most fragile one. But if you understand what I mean, it's just we aren't efficiently architecting our models to perfectly fit the information we're putting in, right? We're picking a model or an architecture that we think is going to have enough capacity for all the information we want to add, and then we're shoving all the information into the model. And when we're doing a method like full fine-tuning, we're targeting all of the weights in the model. So without respect to redundancy, we're just trying to say, learn everything that I give you and be able to reproduce it well. Now, that being said, there are some cool continual learning methods on the horizon that do target more specific areas of the model that don't have as significant contribution or information already stored. So when you're doing this kind of iterative continual learning, you can sort of more explicitly target the areas in your model which don't have a lot of information to add new information into. And that could be a good way of avoiding either redundancy or overwriting information or so on. But the way that we train models right now is blind with respect to redundancy. Like when you're doing full fine-tuning of a model, there is no anti-redundancy built in. You're just simply saying, this is my model capacity. Across this capacity, learn all of the tasks I'm giving to you.
Yeah, and I think in the paper we have some preliminary analysis for the theory. So we have the intuition that these models are over-parameterized. And when you look at the singular value decomposition of these matrices, you see that, for example, for value matrix model, when the value matrix, the value underscore projection matrix, when the maximum singular value in that matrix is close to 0, what it essentially does is it takes the embedding for each token and pushes that to 0. So what would be important in that case is just the residual connection, which is where all the information is being carried. And similarly for query and key projection matrices, when the maximum singular value is close to 0, you just an averaging of the token embedding happens across for the new hidden dimension for the new tokens. So yeah, like we have some preliminary analysis that shows that when these matrices, the maximum singular values are close to 0, they're like pretty much doing nothing, and the only thing that's important is the residual connection.
Yeah, thank you, Nikhil. Also worth noting, special thanks to Nikhil, as well as Hao, Ligong, and Akash for working on this paper as well and helping figure out the Hopscotch method, defining it and experimenting with it. Without this group, it would have been very difficult to get through as much as we did and to be able to develop this method into what it is today. So special appreciation to all of the authors listed on the paper.
Okay, I think if we have any last questions, we probably have time for one more. If not, we can wrap it up.
Yeah. If people do have questions that they think of later, feel free, if you are on Red Hatter, to message me on Slack. If not, just contact me through my email, and I'd be happy to respond and talk further.
Okay,
All right.
thank you.